The chain rule is by far my favorite rule in differentiation, and its proof is pretty simple to do. So it requires a little bit of thought. So first we're going to define this quantity. Epsilon equals delta y over delta x minus f prime of a in this context. Let's just say we have a little curve, and let's say this is our a. So we know that there's a tangent line here. There it is. That's a true tangent line. But remember, to get tangent lines, we always approximate. So we're going to use our approximation from this point. So we're going to say it's about this much. So you see how this line is off a little bit, but it's still relatively close. So epsilon is defined as the difference between the approximation line slope and the real slope. So keep that in mind. This will be important throughout the proof. Next thing we're going to do is we're just going to define all the things we need for the chain rule. So down here. So let's say u equals g of x, and it's differentiable. Let's assume it's differentiable at a. And then we're going to have y equals f of u, and that's differentiable at, we're going to say b equals g of a. Okay? Then we're going to use this formula written in a different way. So let's manipulate this formula so that we can manipulate it so that it looks like delta y equals delta x times f prime of x plus epsilon. And we're going to manipulate these in the same way. So see how here y is f of x, which is why this is f prime of x. This should actually be f prime of a. Sorry, because this was a. So this was a. So we're going to use the same concept for u. So we're going to say delta u equals g prime of a plus epsilon 1, because there's going to be a second epsilon, and all that times delta x. And remember, it's delta x because u equals g of x. And then similarly, we're going to define delta y as equals f prime of b plus our epsilon 2 times delta u, because y equals f of u. Now we're going to take this delta u and substitute in right there, and we're going to do that on the back of this paper. And we're going to get delta y equals delta x times g prime a plus epsilon 1 times f prime b plus epsilon 2. Okay? And now what we're going to do, we're going to do delta y over delta x dividing. Remember, that's starting to look like the slope, so g prime a plus epsilon 1, f prime b plus epsilon 2. Now we're going to take the limit as delta x approaches 0 of delta y over delta x, which is of course dy over dx, the true derivative, and that's going to equal the limit as delta x approaches 0 for g prime a plus epsilon 1, and that's going to be times limit as delta x approaches 0 of f prime of b plus epsilon 2. Now let's take a quick look at the back. As delta x approaches 0, that means our approximation gets closer and closer, which means the error, which is epsilon, gets smaller and smaller. It approaches 0. So as delta x approaches 0, epsilon 1 approaches 0, because epsilon 1 is dependent on, where's my delta u? It's on the back. Because epsilon 1 is dependent on delta x, right? And even though delta y is not dependent initially on delta x, delta y is dependent on delta u. And delta u approaches 0 as delta x approaches 0. So therefore, delta y approaches 0 as delta x approaches 0. And also epsilon 2 approaches 0, because epsilon 2 is the error. So we're going to get these epsilons go to 0. They approach 0. So we're going to get equals g prime of a times f prime of b. And remember, that is saying g prime of a times f prime, and b we defined as g of a. And that is exactly what the chain rule is.